Stanford University.
We're going to begin inflation tonight, too. Hopefully we'll get through baryogenesis. We will get through it because so little is known. No, I'm serious. The basic theoretical framework, modern physics for baryogenesis means the creation of the, I'll explain the words in a moment, but it does mean the excess of matter over antimatter. The modern theory, I will tell you what I know about the history of it. I was engaged in the history of it. In 1980, Savas and I were asked by Bob Wagner, why is there so much entropy in the world? Bob Wagner is a cosmologist at Stanford. Why is the number of photons, which is counting the entropy in the world, why is it so much larger than the number of protons and electrons? Remember, it's about 10 to the 80th times larger. No, 10 to the 10th times larger, 10 to the 8th times larger, 10 to the 8th times larger, approximately. 10 to the 8th, 10 to the 9th, something like that. Why is that? What created all these photons for every proton? We thought about it a little bit and then realized that the question was upside down. The question was not why there are so many photons, but why there are so few protons and electrons. And we basically worked out what the modern theory is. I'm going to tell you what it is tonight. And for a brief period of time, the conditions to explain the imbalance of particles and antiparticles were called the Dimopoulos-Susskind conditions. Somewheres during that time, a little bit later, two young Russian mathematicians came to me, and they said they were writing a book about, or not writing a book, yeah, they weren't writing a book. They were looking for contributions to a book celebrating Andrei Sakharov's career. And they brought me a list of papers about this thick, and would I look through them and see what was interesting and write about it. So I started to look through them, and sure enough, I discovered exactly the same paper. It was remarkably the same as what Savas and I had done, with the exception that it was done in 1967, 13 years earlier. Been lost completely to the Western world. The Russians knew about it, but at that time wasn't a lot of communication between the Russians. And so I did indeed write a little historical paper about Sakharov's contribution and made the mistake of calling them the Sakharov conditions. They are now known as the Sakharov conditions, justly so, of course, that they're known as the Sakharov conditions. And there are basically three conditions that I'm going to go through and explain to you that if they are satisfied, and they are satisfied, then there will be an imbalance of matter over antimatter. The real question is the magnitude of it. Let me say something else. This same kind of question is going to come up later. Is the thing we're asking really a legitimate question? Okay, maybe the world just started with more particles and antiparticles, and end of story. But it focuses your attention a lot when you have a number. When you have a number, a specific number, and in this case, it was the 10 to the 8th photons per proton. Numbers, focuses your attention and says, this number needs an explanation. So the excess in itself was just a fact that you could have said, well, maybe it's just that way. But once there's a number, and in particular, if the number is some oddball number, like 10 to the minus 8th, you start to think maybe this thing needs an explanation. So the explanation of the, yeah.
How does it relate to entropy?
Roughly speaking, for a black body thermal spectrum, the entropy is simply the number of photons. It's just the number of photons. And a black body radiation carries entropy. It's thermal. And to within some factor of order 1, I forget, there's some pi's in it and simple factors, the entropy of black body radiation is just the average number of photons in the gas. So when people speak about the entropy of the universe, in many contexts, what they're often talking about is just the number of cosmic microwave background photons. That's what they mean by it. And so when I say, when Bob Wagner came to me and said, why is the entropy of the world so large? He was asking me why the number of photons per proton is so large. You know, you might have asked, how did that small number of protons make such a large number of photons? But that is not the right way to think about it. As I pointed out to you last time, or time before, in the very early universe, there were huge numbers of protons and huge numbers of antiprotons. And they were basically equal to each other, with the number of protons and the number of antiprotons being approximately the same, or the number of quarks and antiquarks. Same true for electrons and positrons, being approximately the same as the number of photons. Thermal equilibrium at some very high temperature. And then it cooled. When it cooled, the photons were left over. They were left over because they decoupled. The universe became transparent and the photons just hung around, and we see them today. The protons and antiprotons annihilated each other. The universe expanded fairly slowly, and there was plenty of time for them to find each other, by and large, and annihilate each other, and all that was left over was the slight excess. So the question became not why there are so many photons, but why was there this tiny excess of 10 to the minus 8? In other words, the number of protons minus the number of antiprotons. Where is it? This number over here, divided by the number of photons. But the number of photons and the early history of the universe was approximately the same as the number of protons plus antiprotons. Number of protons plus in p bar. And that's a number which is about 10 to the minus 8th. Okay, so there's a number to compute. Why does this small number appear? Now, we don't know what the number, or the reason for the number. And that's because we don't have a complete theory, but almost any theory that we write down which explains it always gives a small number. So we'll talk about a little bit what kinds of conditions are necessary, and it turns out sufficient to make an imbalance of matter over antimatter. Now, is it matter over antimatter? How come it didn't come out antimatter over matter? Well, that's largely a definition. Which one? The thing we call matter is the thing that we're made out of. So that's definition. All right, let's begin with a hypothesis which is really believed to be wrong, but we'll come to it. Namely, that baryon number. What does baryon number mean? If there are only protons, baryon number can be interpreted in terms of quarks. It's basically the number of quarks minus the number of antiquarks in the world. I think it's 3 times that to be exact, and the reason it's 3 times that is because it was originally defined in terms of protons and neutrons being baryons, and a proton and a neutron has 3 quarks in it. So that's called B, the baryon number of the world. Number of quarks minus the number of antiquarks times 3. If all that exists... Say it again?
1/3? 1 divided by 3.
Yeah, divided by 3, thank you. Divided by 3. Or 3 times the baryon number is, yes, you caught me, divided by 3. The baryon number of a proton is 1, and it has 3 quarks in it. Good. Okay, so that's called baryon number. And there are other kinds of objects that carry baryon number besides protons and neutrons. But they're all unstable. Even the neutron is unstable. Nevertheless, there are other kinds of objects. We can mostly focus by thinking about quarks themselves, if we like. And the statement that there's a baryon excess is the statement that there were in the early universe more quarks than antiquarks. The number of quarks and antiquarks separately were about the same as the number of photons. And so the question is how it got that way. Okay, let's suppose for the moment that baryon number is like electric charge. One of the things about electric charge is that it's conserved. It doesn't change with time. Now, baryon number is not like electric charge. Electric charge is the source of Coulomb forces, long-range electric fields which create long-range electrostatic forces. Baryon number itself is not a source of some kind of Coulomb-type force. Of course, the protons are electrically charged. Therefore, they make conventional Coulomb forces between each other. They make electric fields. The neutrons are not electrically charged. They don't make electric fields. So what we would say is it's the charge of the proton, not the baryon number of it, which is creating any kind of long-range field. And baryon number itself may be conserved, it may truly be conserved, but it is not exactly like electric charge. It doesn't exhibit this tendency to make long-range forces. All right, but suppose it's conserved. Suppose it's conserved. Then, if there is ever an excess in the beginning, let's say, of the universe, whatever that means, then there will always be an excess, and that excess will be sort of frozen in. If you change the number of quarks, you must change the number of antiquarks by the same amount if baryon number is conserved. And what's more, experimentally, baryon number appears to be highly conserved. Nobody has ever seen a proton disappear. We can talk more about experiments which search for the decay of protons and so forth. But the first approximation in our world, protons are extremely stable. What could they decay to? Let's ask a question. What could they, suppose a proton was to decay, what could it decay to? It must decay to things which are lighter than itself. Okay. It must decay to something which has a positive electric charge. So if a proton were to decay, and must, if we want to assume that whatever it decays to is stable, there's really only one thing that it could decay to. It could decay to a positron and something electrically neutral. A proton could decay, a proton could disappear and become a positron. That conserves electric charge. It doesn't conserve energy. A positron is much, much lighter than a proton, but it would compensate by giving off a neutral particle. What kind of neutral particle is around? Photons. Photons are a prime candidate. So a decay possibility for the proton would be proton, I'll draw it as a kind of Feynman diagram. A proton moving along would decay to a photon, which we'll call gamma. Photons are typically called gamma. And an electron antiparticle, E+. That's a possible thing that could happen, and we don't really know any deep fundamental reason why it can't happen. And maybe it does happen. We're going to talk about whether it does happen. In fact, we think it does happen. But for whatever reason, yeah.
What about a neutrino?
Oh, no, it can't decay to you mean a positron and neutrino? Yeah. No, no good. No good. Okay. A neutrino is a fermion. 2 fermions make a boson, and a proton is a fermion. So whatever the proton decays to, it must decay to something with an odd number of fermions. Okay, so it can't decay into a positron and a neutrino. Right, yeah.
If baryon number really was conserved, it would correspond to a symmetry of some sort.
Yes.
Was there a candidate for that, or has no one ever found one?
You can always, given any conserved quantity, you can always make up a symmetry that, but then you can say, well, all right, is it really a symmetry? And the way to test it is always to ask whether baryon number is conserved. So it's a little bit circular. But yes, you're right. If baryon number was conserved, it would correspond to a symmetry, and if it's not conserved, it doesn't correspond to a symmetry. Okay, yeah.
Is there, should you think about particles decaying and particles annihilating with each other as sort of different things, like a proton can annihilate with a positive, with a negative proton?
Yes.
So is that, can you think of that as a decay or not?
No, that's not a decay. It's not a decay of the proton. It's just called annihilation of a proton. But the important point here is that the baryon number doesn't change. 3 quarks and 3 antiquarks came together. The sum total, the baryon number is 0. And afterwards, it's just a bunch of photons, and the baryon number is still 0. So, right. So that's a fair question, but it does. And you could call it a decay if you wanted to, but it wouldn't correspond to a right. Okay. So for whatever reason, and we don't know the reason really fully, the standard model does not permit this decay. Incidentally, doesn't happen in the standard model. But there are versions or extensions of the standard model which are perfectly viable, in which this process could happen. Now, one thing we know about it immediately, the decay rate of the proton cannot be very large. Our protons have been around for 15 billion years or whatever it is, 13.7 billion years, and they haven't disappeared on us. So if the decay time of the proton were a microsecond or even faster, which particle physics might permit, the protons just wouldn't be here anymore. So the lifetime of the proton is at least very, very, very long. But in fact, it's much, much longer than is necessary for the protons to still be here. The mean lifetime of a proton is more than 10 to the 32 years, so it's very long. And we don't completely understand why. In fact, we don't understand why at all, but we take it as a fact. A fact, at least a temporary fact. Let's assume it for the moment. That would mean that the total baryon number in the universe, but let's just say in a box, doesn't change. And so the only theory of this excess that we could have is that it was built in from the very beginning, and it still survives today. That would be a consequence of baryon conservation, baryon number conservation. I'm not saying that's true. I'm saying that's a consequence of baryon conservation, that this is the same today as it was at the very beginning. Now, there's another symmetry of nature, which again is not really a symmetry of nature, but you might have thought about it as a symmetry of nature. At the time that Sakharov put out his theory, it was only a couple of years after it was discovered that it wasn't a symmetry. We'll talk about it. But it's particle-antiparticle reflection symmetry. The statement that particles, if interchanged with antiparticles, that you can't tell the difference. Of course, you can tell the difference between a proton and an antiproton, because we're made out of protons. But if we changed all of our protons to antiprotons, if you were made out of antiprotons and I was made out of protons, don't get too close to me, and somebody showed me a proton, I would say, yes, that's a proton. Somebody showed you an antiproton, you would have exactly the same response. I mean, you would see the same thing that I saw. That's called particle-antiparticle symmetry, or reflection, charge reflection symmetry. And for technical reasons, well, all right, that's a symmetry. It's not a symmetry. But up until around 1964 or 65, I forget exactly when, it was thought that charge conjugation symmetry, this is called C equals charge conjugation symmetry. It was believed that it was a symmetry. Particles go to antiparticles. Two other things which were thought to be symmetries of nature, which went along with this, were called P, which is P is for parity, but it has nothing to do with economics or fairness. It's left-right symmetry, mirror reflection symmetry, that if there's a kind of particle which exhibits a handedness, for example, it rotates to the right when it moves forward, spins to the right when it moves forward, then it had been assumed that there would be a left spinning particle which also moves forward, left-right symmetry, and that was called parity. And the final interesting symmetry for us tonight is called T, and T is time reversal. What this means is that any process that can happen in nature, just an ordinary let's restrict ourselves to laboratory processes, let's not worry about the whole universe. Any process that can happen in nature, we could take a movie of it. If we run it backwards, it is still a possible thing that can happen. Anything that can happen, the opposite can happen. Now, it doesn't seem that way when you think about the real world, of course. The second law of thermodynamics says things get worse. But at the microscopic level, at the true microscopic level, we don't average over things and we don't do statistical averaging and so forth. Any process that happens in nature was thought that its time reversal was another possible thing that could happen. That's called time reversal symmetry. Now, what is actually known mathematically, this is a mathematical statement about quantum field theory, which I am not going to try to prove tonight. It's a hard theorem, but it follows from the basic structure of quantum mechanics and relativistic field theory, is not that charge symmetry is a symmetry, particle-antiparticle, not that parity reflection symmetry is a symmetry, or that time reversal is a symmetry, but the product of all three of them, CPT, and I'll tell you what that means in a minute. CPT is a symmetry. And this, for mathematical reasons, fundamental mathematical reasons, which you'll have to accept for now, is not consistent to not have this symmetry. Now, what does a symmetry mean? It means if you take any process, replace every particle by its antiparticle, reflect it in a mirror, and run it backward, it is still a possible process in nature. Okay? You have to do all three in order to be sure that it's a symmetry. Up until the 60s, yeah.
So for a wave function, you can't just change the sign of t.
No, you have to complex conjugate it too.
So does time reversal always mean take the complex conjugate as well as change the sign of t?
Mm-hmm. 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 Right. Yeah. You can see that from the Schrodinger equation. The Schrodinger equation is something like I d psi by dt equals, I don't know, d second psi by dx squared or something like that. That's not quite right. But supposing you change the sign of t, that changes the sign of the left-hand side, but it doesn't change the sign of the right-hand side. So changing the sign of t doesn't work. But if at the same time you complex conjugate and change the sign of t, which also requires you to change the sign of I for complex conjugation, then it does work. But this is something we don't need to get into right now. CPT is a symmetry. But let's suppose for a moment, let's go back to Sakharov, or even before Sakharov, before the facts were actually known. Let's suppose that either charge conjugation or C times P, which is the usual one that people focus on, that was a good symmetry. C times P means change every particle to its antiparticle and change your left hand with your right hand. That was actually thought to be a good symmetry of nature. That would entail that there's some kind of symmetry which allows you to change the sign of every particle to its antiparticle. You'd also have to change left to right, but that goes along for the ride. If you believe that, then you might ask, well, gee whiz, if there is a complete symmetry between particles and antiparticles, why should it be that at the very beginning there was an imbalance of one versus the other? Now, nobody can tell you that there isn't an imbalance. It just dates back to the very beginning. But you might also wonder, what's going on here? The laws of physics seem to be completely symmetric between the two kinds of things, particles and antiparticles. And yet, for some reason, there was this small imbalance of size 10 to the minus 8. It doesn't sound right. Okay? All right. The modern theory of baryogenesis begins with the idea that there was a balance, that particle, antiparticle were balanced, again, not for any good reasons, but just for whatever initial condition you started with, there was no bias toward particle or antiparticle. That's an assumption. It can be justified in some frameworks, but it's all right. So then, how is it possible then that it got imbalanced? The only way that it's possible for it to get imbalanced is if the conservation of baryon number is not correct. In other words, if processes can happen, and here's one, if processes can happen in nature in which a proton becomes a positron, that is a violation of baryon conservation, which allows the baryon number of the universe to change. That would be the first requirement for a theory of baryogenesis that was based on the assumption that the starting point was balanced between the two. That if you're going to wind up with an excess of quarks over antiquarks or baryons over antibaryons, baryons meaning protons and neutrons, you must have a mechanism which violates the conservation. So that was Sakharov's first condition. Condition number one, Sakharov conditions. Sakharov conditions started with number one, baryon number violation. Violation means violation of the conservation law. And as an example, the process of a proton becoming a positron and a photon is an example, okay, if it happens in nature. That was condition number one. Let's just talk about that for a minute. If baryon number conservation is not a good conservation law of physics, then it must be a very, very weakly broken one. As I said, protons are very old. They didn't disappear. So it must be very old. It must be very old. The protons are old. And whatever mechanism, such as this kind of decay, it must have a very, very, very small probability per unit time. One can ask in current theories, current unified theories, most of whom, in fact, everyone, no, I take that back. Every known unified theory, and even when they're not unified, if they're coupled to gravity, every known fundamental theory violates baryon conservation like this. you can ask, in the known theories, why is the proton so stable? And the answer tends to be something like this, that the theory has Feynman diagrams, has processes in which the proton comes in from the left, meaning from early, out goes an electron, out goes a photon, but somewhere in the guts of this Feynman diagram, there are all kinds of particles. Let's not specify exactly which ones are in there, but among them, assume that there's at least one or more particles which are very, very heavy. In other words, that it requires a particle type which is very, very heavy in there. Particles which have not been discovered yet. Now, one of the reasons to believe this is that the Standard Model by itself, with its ordinary known particles, does not permit this to happen. And so in order to make it happen, you would have to have new additional particles that were not part of the Standard Model. And that certainly means that they're heavier because they haven't been discovered yet. But imagine making them very heavy. How heavy? Oh, 10 to the 16th GeV, or 10 to the 16th times heavier than a proton, which is not an unnatural number for heavy particles. Then what's true is that this kind of process is extremely unlikely. Extremely unlikely means that the quantum mechanical amplitude for it is suppressed by inverse powers of this heavy mass. Typically, for example, it might be, let's call this the heavy mass m. The Feynman diagram will contain a 1 over m squared just because it's so hard to make a heavy particle. Just because it's so unlikely, that heavy particle doesn't last very long. It has to melt into the rest of the Feynman diagram. But if the particle is heavy enough in there, then this will be a very, very small probability process. That's the kind of thing which keeps the proton stable in modern unified theories. I don't know if it's right. I'm not saying it's right, but this is a mechanism that the extra particles that are there are all heavy enough that they suppress this enormously. All right. Now, I will tell you something else. That this 1 over m squared, if for some reason the proton is given a lot of energy somehow, then this isn't really 1 over m squared, but it's really some energy, m minus some energy squared. If the proton has excess energy from some other place, this can well be a much smaller suppression, and I'll tell you where that extra energy comes from in a minute, where it can come from. But in the ordinary world, a proton sitting around, there's nothing to give it an enormously heavy kick, an enormously high kick. It doesn't have a huge amount of energy. Protons, when they collide or anything else, don't have huge amounts of energy. So this is where you begin. And theories of this type can explain why the proton is so stable. Of course, you could say they don't explain anything. They just tell you that for some reason that that the particles which could cause which are necessary for the proton decay must be very heavy, and that's true.
This extra energy, is that not included in MC squared?
Yeah, any energy that's not included in its rest mass squared. Nevertheless, we go in here, and I'll tell you where such energy can come from in a moment. But as I said, all theories, all known theories, and I would venture to say any theory that ever will exist, will have the possibility of baryon violation. Okay, so let's agree tentatively that baryon violation is not taboo, that processes such as this can happen. They're not forbidden by any fundamental law of physics. It's just an accident of the particle spectrum that the proton is as stable as it is. Let's take that as an assumption, a working assumption. Baryon violation by itself is not sufficient to to give you an average excess of protons over antiprotons. Why not? Because for every event, where is it? Every event like this which can happen, which can cause you to lose proton number. This is a source of decreasing baryon number. You started with 1 unit here and you have no units over here. For every process like this, there is the charge conjugate process in which an antiproton comes in, a true electron goes off, and the antiparticle of the photon is the photon. The antiparticle of a photon is itself. So, if we believe in particle-antiparticle symmetry, then for every process like this, a process like that happens, and on the average, there will be as many of these kinds of decays as these kind of decays. So if we started out, with an equal population of quarks and antiquarks, of baryons and antibaryons, and we try to rely only on the violation of baryon number, it would not be a very efficient way to create an excess. What do I mean by that? I mean, think about it for a minute. Supposing there was a randomness that, let's see how to say this. I might add something else, incidentally. That in the very early universe, there were lots of electrons, positrons, and photons around, and it's perfectly possible for the opposite to go. An electron, a positron and a photon can come together and make a proton. An electron and a photon can come together and make an antiproton. So there's a statistical balance of things going on. It's only statistical that there would be as many protons as antiprotons, because these processes are statistical processes. But the imbalance of protons over antiprotons is not a statistical effect. Yeah.
Quick question on that lower diagram. On the left-hand side, is the baryon number equal to -1 there?
Here, yes. -1 goes to 0. Yeah. And, right. -1 goes to 0. Here, 1 goes to 0. And the reason that it can't be a statistical effect is that it is quite true that the baryon excess is a small number, 10 to the -8. Okay? But you ask, how many protons are there in the entire universe, known universe, observable universe? And the answer is about 10 to the 80th. How big would you expect the excess of protons over antiprotons to be if it were simply a pure statistical effect? Square root of n. Right? You know that the statistical fluctuation in a variable, just due to random statistics, is of order the square root of the number. If you have a random heads tails flips, and you collect let's say 1,000 flips, the number of heads will be 500, but that's up to the margin of error. And what is the margin of error? The margin of error is the square root of the number of flips. And so you expect that in the number of flips, the number of heads will be 500 plus or minus, what's the square root of 500? 25? 500, margin of error will be about 25. Okay, now let's come to the world which has 10 to the 80th protons in it. What is the margin of error, or the statistical fluctuation, the average expected statistical excess of protons? It would be square root, which would be 10 to the 40th, right? 10 to the 40th. 10 to the 40th over 10 to the 80th is 10 to the -40th. So if the excess was 10 to the -40th, we could say it could be statistical. But it's not. It's much, much bigger than that. Yeah.
It depends on the number of protons and antiprotons in the very early universe that became our observer.
I'm assuming that they started out balanced.
Right, they started out balanced. And if there were 10 to the 160th
Yeah.
protons and antiprotons in that early universe, then the spur of that could be 10 to the 80th.
It could be. It could be. The other thing that would be very hard to justify, extremely hard to justify, is if it was statistical fluctuation, why it would be the same everywheres. Okay, that would be very, very hard. Right. Right. You'd expect a patch over here with protons, a patch over there with antiprotons. And so you can ask, what is the experimental evidence that neighboring or even very distant galaxies are not anti-galaxies? And as I understand it, there's very good evidence. The good evidence is if the population of galaxies was sort of symmetric between galaxies and anti-galaxies, then you would expect cosmic rays, especially very high energy cosmic rays, which are thought to be cosmic in origin, to have as many nuclei as antinuclei, or as many antinuclei as nuclei. We do see, for example, helium nuclei in cosmic rays. Okay? As I understand, nobody has ever seen an antinucleus in cosmic rays. You do see antiprotons, but that's fairly easy to explain. Even if we didn't have any cosmic rays, antiparticles coming in, when a high energy particle would hit the atmosphere, it would make antiprotons. But it's extremely difficult to make an antinucleus. That would take an incredible piece of luck of a very high energy collision with the atmosphere, creating an antinucleus, not likely. So the complete absence of antinuclei strongly suggests that the universe is not equally populated with galaxies and anti-galaxies. So there's something to explain. It's not statistical, and we need to explain it.
Do you see helium nuclei, or do you just see energies that look like they trace back to helium?
I believe you see helium nuclei in cosmic rays directly. Yeah, yeah. And you know, the detailed statistics of it, I don't know. It's not my field of physics, but that's where the argument lies, at least one of them. Okay. We also don't, there's another thing we don't see. If our galaxy, for example, was particles, and the Andromeda was antiparticles, then in the region in between, you would expect there to be both particles and I mean, there's plenty of electrons around, for example, circulating around in the region between galaxies. You would expect there to also be plenty of positrons. And then you would expect there to be lots of positron-electron annihilations. And positron-electron annihilations are very easy to detect. They produce pairs of photons of very definite energy, and those pairs of photons could be observed. And it's not that we don't see electron-positron annihilation, but we don't see nearly enough of it to account for the possibility that neighboring galaxies would be anti-galaxies. So that's almost certainly ruled out that there are anti-galaxies out there, and certainly ruled out that there's an equal population of them. Okay, so particle-antiparticle symmetry tends to suggest rather strongly that the universe was created symmetrically, although it doesn't prove it. And so the next element of the argument is that in order to account for the fact that there are more protons than antiprotons, this charge conjugation symmetry must fail. The idea that, that particles and antiparticles are symmetric in the laws of physics. And that the charge conjugation times parity, it's enough that it would be bad enough, charge conjugation or charge conjugation together with anything else, any symmetry that involved interchanging particles and antiparticles. If you had that symmetry, you would have a very hard time explaining. Another way to say it is if we allow baryon violation, that's not enough. That will just give you the statistical effect. You need something to push it in one direction. You need something to bias it toward particles rather than antiparticles. You need something in the laws of physics that will cause this baryon violation to be biased so that one kind of thing happens more than the other. The implications of that are that you need violations of particle-antiparticle symmetry. In particular, this so-called CP symmetry, but it's basically just particle-antiparticle symmetry. Again, is there particle-antiparticle asymmetry in the world? Yes, there is. We know with absolute certainty, experimentally, that particles and antiparticles don't behave the same way. A particular example, it's rather, the examples are hard to come by, but once you have one, or two, or three, you know that the laws of physics are not symmetric between particles and antiparticles. The simplest example to explain is the so-called B meson. A B meson is a particular kind of particle made of a quark and an antiquark. It's made of a it's made of a bottom quark and an anti-down quark. A bottom quark and an anti-down quark. Bottom quark and an form a meson. They form a meson. The meson is bound, and it's called the B particle. Now it has an antiparticle. You just interchange the bottom quark for the anti-bottom quark, and the anti-down quark for a down quark, and you get the anti-B meson. Both the B meson and the anti-B meson are electrically neutral, but they are not their own antiparticles. This one is made of B quark and anti-down quark. This one is made of anti-B quark and down quark, or whatever the opposite was. Right. These particles decay, and they decay into pi mesons. Let's see, this one, I always forget. It takes, I'll just write it. I'll just write down one possibility at the. Oh boy, I've forgotten what a B meson decays in. They decay into lots of things, but a charged. Oh, I know. They decay into a K meson and a pi meson. And I think the B meson becomes, I think it's a K plus and a pi minus. This is not important. The fact is that there's a very definite decay into a K meson and a pi meson. The B meson is electrically neutral, so the decay products are electrically neutral. That it follows that the anti-B meson can decay into the antiparticles, which is a negatively charged K meson and a positively charged pion. The only important thing is that it's a process in which a particle can decay into other particles versus a process in which the antiparticle can also decay into its antiparticles. Now, these are the rates for these things to happen are measurable. They are measured, and they are different. They are different. One of these, I can't remember which one, is about 2/3 more important than the other. And so it's in this case, it's a fairly gross violation of particle-antiparticle interchange. It's definitely a real effect. There are lots of indirect measurements. This has been known for a long time that particle-antiparticle symmetry is not a good symmetry. It's not a symmetry. One is fed. Now, once this can happen, we can, meaning to say that there are fundamental processes in nature buried deep inside Feynman diagrams somewheres that are imbalanced between particles and antiparticles. It's no longer the case that this decay and that decay have to have equal probability. There is a rule that the total decay rates, the total half-life of the proton and the antiproton have to be exactly the same. That's a theorem for relativistic field theory. But the way that these two can be different from each other is there's more than one way that a proton can decay. A proton can also decay, for example, into a mu plus and a photon, and an antiproton can decay into a mu minus and a photon. And what the theorem says is that if you calculate all of our possible ways that the proton can decay, and you consider the half-life or the total rate of decay of the proton, it must be exactly the same as the total rate of decay of the antiproton. But what it does not say is that the decay rate of the proton to electrons or to positrons and photons must be the same as, you know what I mean. It doesn't say that any particular decay has to have a symmetry. In particular, if at some fundamental level this charge conjugation symmetry is violated by something in the theory, then it will allow this to not equal, let's say this here, not equal to, that's a special symbol I just invented, not equal to, it allows that, and not only allows it, basically insists that these two not be the same. Once that's true, it says there's a bias. Somewheres in the laws of physics, there is a bias toward either protons or antiprotons, or matter versus antimatter, some kind of bias. And that's something which is absolutely necessary to add to baryon number violation, to give it a directionality, to give it a push in one direction rather than the other. So Sakharov's second condition, incidentally, I think Sakharov's paper was I've forgotten when CP violation was first discovered, but Sakharov's paper was very quickly after that. When the CP violation, the particle-antiparticle symmetry was discovered to not be correct, within a year or so, I don't remember exactly, Sakharov wrote down his basic conditions. So that's number 2. C and CP, or particle-antiparticle asymmetry in the laws of physics. This is expected in any theory that we know. Any theory that we've studied for particle physics always has, and including just the standard model. In fact, I said something wrong. The standard model does allow baryon violation. In fact, it not only allows it, it insists on it at some level. So every theory that we know about, but as a theoretical statement, insists that baryon number violation happens. Experimentally, we know that CP is violated and particle inversion, particle-antiparticle symmetry. Now, there's one remaining, yeah.
So if the total decay rates are the same, then why don't we have equal numbers?
Because the mu particle is heavier than the electron. So we could be in a situation where for example, where it's hot enough to, what I need to explain to you is first why this can happen rapidly, even though I said that the proton is very stable. It has to do with the environment. Let me come back to it. It's a good question. All right. How do we overcome the fact that the proton is so incredibly stable? Remember what I said, the proton lifetime is something like about 10 to the 33, 10 to the 34 years or longer. The universe has only been around for 10 to the 10th years. So on that scale, the proton is very stable, and why don't we get to ignore this kind of thing? And the reason has to do with the fact that the universe in its very early stages was very, very hot. Because it was very hot, the protons, or the quarks in particular, we can substitute quarks here, it doesn't matter, because it was very hot, they were constantly engaged in very, very high energy collisions. The high energy collisions meant that the protons moving in this plasma, in this very hot gas, had lots of energy. How much energy? It depends on the temperature. But at some temperature, you get to a high enough point where the average kinetic energy, the average extra excitation energy of the proton is high enough so that even these heavy particles here do not suppress the proton decay or the baryon violation. In other words, to put it short, a proton at rest, forget at rest. A proton in an environment where it isn't constantly being knocked around and having an enormously large excess energy of some kind or another is very stable. But when it's heated up to a high temperature, a high enough temperature, this excess mass here is not an important factor, and the proton decay would happen quickly. So if we go back to the very early universe, when the temperature was very hot, then these kind of processes can happen. Now, this statement that the total decay rate is the same for protons and antiprotons is a statement about zero temperature. It's a statement about a proton at rest in an environment where it has no excess energy. When it's being kicked around and when it has extra energy, then that is not necessarily the case. In fact, it's generally not the case. In an environment which has some energy around, which is kicking the protons around, the decay rates don't have to be the same. So, that is not a problem. The problem has to do with the CPT symmetry. I said that there was no particle inversion symmetry, but there is a symmetry, at least in all known quantum field theories. In all known quantum field theories, string theories, any theory we know how to write down, which has relativity and quantum mechanics built into it, charge conjugation times reflection times time reversal. Again, what that means is you exchange every particle for its antiparticle, you reflect in a mirror, and you run the film backward. That is a symmetry of all theories. All right. So, what does that mean? That means, among other things, that in thermal equilibrium, if the universe was just static, if it wasn't changing but it was hot, in thermal equilibrium, forward time is the same as backward time. In thermal equilibrium, backward and forward in time are the same thing. There's no asymmetry of time reversal. So in thermal equilibrium, where the universe is not changing, an imaginary universe which is just a pot which is there, a hot pot, it would have time reversal symmetry. If it has time reversal symmetry, and it has C times P times T, then it must have CP symmetry. All right. CP just means particle change to antiparticle for our purposes. If particle goes to antiparticle and time goes to, I was going to say anti-time, and time goes to minus time, if that's a good symmetry, but the world has no bias toward one time or another, then you're stuck again. You're back to having a particle antiparticle symmetry, and you cannot have a proton antiproton excess in thermal equilibrium. That's a theorem. That's a theorem that's been known for a long time, that in thermal equilibrium, that the thermal equilibrium will come to a configuration with equal numbers of protons. But the universe was not in thermal equilibrium at early times. It was expanding, and it was expanding fast at early times. It was expanding fast enough that it could not be considered in equilibrium. If it's not in equilibrium, that means that forward time and backward time are different. That's the reason. If the universe is expanding, forward time and backward time are not the same. So in a rapidly expanding phase of the universe, we don't have to worry about time symmetry. It is definitely not symmetric. If time symmetry is broken just by the expansion of the universe, then we're in business. Then we have enough asymmetry of all possible kinds that the baryon violation allows a change in the baryon number. The CP violation allows a directionality for it, and the out of equilibrium.
Can you define what that exactly means?
Yeah, it just means things are changing rapidly in a particular direction of time. It means the universe is expanding fast enough, that's all it means. So that running the thing backwards does not look like the original thing. In a world where the universe is running in one way, namely expanding, it is out of equilibrium. Okay. Being out of and it has to be enough out of equilibrium. It's not enough for it to be very, very slowly expanding. It has to be expanding rapidly enough that these microscopic processes don't have a time to adjust themselves to the equilibrium configuration. But whatever it means that backward and forward times are different. That a picture of the universe, that a movie of the universe allows you to tell which way is forward in time and which way is backward in time, just by the expansion. And the fact that it's cooling, the fact that at early times it suddenly cooled rather rapidly in the beginning, that's enough to completely ruin the time reversal symmetry. And if the time reversal symmetry is ruined, the CP symmetry is also going to be ruined. So those were the three conditions of Sakharov. All three are believed to be really satisfied in the real world. And it's also believed that they are enough, that if all three of these are true, that there's really just no way it would be a complete accident with no rationale to it if there wasn't some excess created. The problem is that nobody knows enough about the physics of the early universe and the physics of very high energy collisions, the physics of very, very hot temperature, the nature of the particles that are in here, the details of what drives the CP violation and so forth. Nobody knows enough about it to be able to make a calculation of what the imbalance is of protons to antiprotons. That simply we don't know enough. So what we know is all three ingredients that are both necessary and probably sufficient to explain an imbalance, those are there, but the ingredients needed to make a computation to show that this number is 10 to the minus 8th times NQ plus NQ bar, oops, that's out of range. We don't know how to do that. That's the status of this, this particular problem. As I said, it's called baryogenesis. And it will await a much more detailed theory of both early cosmology and particle physics at very high energy. Any questions about that? We are now finished with baryogenesis.
So, but the fact that we know that we have a measurement of 10 to the minus 8th, I imagine that puts some constraints on what these theories could look like.
It does. It does. It does. It does, but they're hard to use. You're right, but to my knowledge, nobody has used it in a really effective way to constrain things. Just too many variables, too many things to.
Map out a neat-looking subspace.
Yeah, Right, of hundreds of parameters. We just don't know enough, yeah.
Now, the connection between that and the positron, electron numbers that you got previously, is that this asymmetry here which allows that to be connected? I don't understand how the matterness of the quarks and the matterness of the electrons are connected.
Every time a proton disappears, a positron appears.
That's an antimatter particle.
That's an antimatter particle. So the loss of baryon number must be made up for by an increase in, right. Or the increase, anything that increases P will decrease. So as long as all of the processes that you're thinking about conserve electric charge, there's no alternative to the statement that if the baryon number shifts one way, the electron excess must shift the other way. Right. Yeah.
I've heard claims that in the standard model, the CP violation that we see in the standard model is not big enough to explain the baryon excess.
I have heard claims like that too.
Oh, you don't believe them?
No, I do believe them. I have no reason not to believe them. I just am a little bit skeptical that anybody really knows how to do the calculation.
I thought that was one of the big reasons why we needed a beyond the standard model.
I'm a little bit skeptical. You know, my involvement in this ended with stating these three conditions, and then thousands of people, not thousands, maybe tens of people, started to try to make computations based on standard models. Stephen Wolfram was one of them, and he invented Mathematica, I think, to do the calculations. Well, you know, I looked at it and I said, look, there's no way that they're going to be able to do this because there are just too many unknowns about the early universe and so forth. So it may be correct, and I don't know. I haven't followed this this story for a long time. It may be that that we know that CP violation in the standard model is too weak to drive. But once you admit CP violation into the physics altogether, there's no reason to expect that at high energy it might not be, tens and hundreds of times larger. Once you've opened the door to it so that it's no longer a principle, then you don't have really much control.
The other thing from these two, if you had equal numbers of protons and antiprotons in the initial universe, all the electrons that we see today in our universe came from the antiprotons.
Well, I'm not sure that's right. I'm not sure that's right. There could have been a population in the very beginning which was balanced between. Oh, I see what you're saying. Well, in that sense, yes. I'm not sure. You could have done the whole analysis in the opposite way by thinking about the electrons instead of the protons, and
Leptogenesis or baryogenesis, and then they balance out.
right, exactly. The word, the lingo baryogenesis is a sort of historical relic, yeah.
Well, because we observe, in deep space, we observe atomic spectra.
Wait a minute, wait.
Well, so those are baryons. We're counting baryon, that's why term.
It has to do with the fact that we don't know how many neutrinos are out there, that people focused on the baryons, but don't worry about it.
Have we had, was the 10 to the minus 8 is today's number and has always been the number? Because what I'm getting at is
10 to the minus 8 is today's number for the ratio of baryon number of protons to photons. Right?
But has there been a period where there was a lot of annihilation of protons and antiprotons?
There was a period when there was a lot of annihilation between protons and antiprotons. It basically removed almost all the protons and antiprotons. But that was the point at which the temperature fell low enough that processes that would create protons and antiprotons, see, at very high temperatures, there's very high energy photons. Two photons come together and they create, one way or another, a proton and an antiproton. Those photons have to have enough energy to create a pair of protons. That means they have to be at least 2 GeV worth of energy. As long as the temperature is high enough, these things are going on backward and forward in equilibrium. Right? As long as there are enough high energy photons around to be able to cause the proton-antiprotons to appear. And it goes the other way. But then when the temperature falls below a certain threshold, there simply aren't enough high energy photons around to create protons and antiprotons, but protons and antiprotons can create photons. Photons are massless. Protons and antiprotons have lots of energy. It can go this way, but it has a hard time going this way. So once the temperature falls below that threshold, the protons start annihilating each other, but there's not enough energy of course, when a proton and an antiproton collide and make photons, those photons have a lot of energy. But then they just go out into the soup and their energy gets lowered by coming to equilibrium with the lower temperature background stuff. So as the temperature goes down, the number of available high energy photons decreases, and you can't make the proton-antiproton, but you can go the other way. So at that point, that's when the annihilation starts, and eventually all the proton-antiprotons get eaten up.
When did this process stop?
When there were no antiprotons.
And that was approximately?
Oh, that was pretty early. Yeah, that was quite early. That was before nucleosynthesis, temperatures in the GeV range. I'm not sure exactly when it stopped.
Before that 300,000 year thing when it became.
Oh yeah, before the first 3 minutes for sure. Some seconds maybe, I'm not sure. We'd have to go.
In an earlier lecture, we were counting up the energy of the universe, and there were 4 different types. There was photons, and there was matter, and dark matter. And the contribution from photons, if I remember correctly, was negligible.
Today?
Yes.
Today.
Right. So after all of this annihilation went on, and this early matter was turned into photons, where did all those photons go if they're no longer around now?
They are around.
Okay.
They're the cosmic microwave background. There's 10 to the 8th of them for every proton.
But how is it that it can account for such a negligible portion of the total energy in the universe?
Because remember that radiation energy density decreases like 1 over the scale factor to the 4th power, and matter energy density decreases like 1 over a cubed. Right.
So if we need this very massive particle to make this work, does that mean the standard model is incomplete?
Yes, it does. Yeah. Right.
Your top 2 diagrams there where you have the unequal sign.
Yes.
Very unequal, and you started with all P's and
Say it again. Say it again.
if it's very unequal and you started initially with P's and P bars, then the P bars would decay because it's very unequal into the E minuses, then you'd end up with the E minus P equivalents for equality. So you started with just all P's and P bars
Yeah.
and no E's.
Uh-huh.
As the P bars go through that second process, then you would get E's equal to P's.
Oh, I see what you mean. Yeah. Yeah, it's, yeah. Yes. You could try to make a theory that way. I think you'd quickly flounder on the fact that at some point the universe was very hot, And at that point, there were these loads and loads of p's and p bars. At least if you wanted to follow standard thinking about what's that? It's very hard to explain why it would be that unequal, particularly since CP violation is a small, very small thing. So it'd be very hard to understand why it would be grossly unequal. And keep in mind that these decay rates, yeah, are very small, but okay, I want to move on. That's what's known about matter-antimatter imbalance in the universe. And as I said, I don't think it's going to be too soon that we know a lot more. All right, now, the next thing we want to move on to is inflation. Inflationary universe. The inflationary universe idea was put forward to explain another one of these things which it's not entirely clear needs to be explained, or wasn't entirely clear that needed to be explained at the time. And the question was, why is the universe so terribly homogeneous and isotropic? This became a rather critical issue when the cosmic microwave background was discovered, and the cosmic microwave background quickly became a rather high precision thing. The high precision thing being that in short order, the black body curve had been measured. The temperature of the cosmic microwave background had been measured carefully. It was known to be about 2.7 degrees and with some precision. With some, the error bars were fairly small. Today they're microscopic. Today the error bars are just, they can't be seen on the, okay. So the temperature was very well defined, looked like a Planck distribution, like a black body distribution. Almost exactly, or exactly as far as you could tell. But moreover, it was the same in every direction. So suddenly, this rough idea that the universe is isotropic became a high precision idea. Now this took years. I'm condensing history into something smaller. But at least by today, in any case, the idea that the universe is isotropic is a very, very high precision thing. So you can ask, why is the universe so isotropic? Today it's isotropic. Must have been isotropic very early. No particular reason why an anisotropy, a lumpiness in the distribution would decrease with time. In fact, quite the opposite. Lumpiness tends to increase with time because of gravity. Gravity tends to take lumps and magnify the magnitude of the lumps. So it means the universe must have started very early being extremely homogeneous and isotropic. When I say very early, I mean at the time before there were galaxies, before there were planets, at a time that the black body photons originated. In other words, at the decoupling time, the universe was extremely isotropic. Now, it was of course known that it couldn't be completely isotropic or homogeneous, let's say. If it was exactly homogeneous, it would stay homogeneous. Anything which is exactly uniform and allowed to evolve will stay uniform. And the universe is not uniform. It's full of galaxies, and it's full of clusters of galaxies. It has a lumpiness that's there. The lumpiness that's there clearly was much smaller to begin with, smaller in magnitude, for the simple reason that lumpiness tends to increase with time. Let me just explain what I mean by that. If you start with a world which is completely uniform, of course it stays that way, but let's suppose there was a little bit of overdensity here. A little bit of overdensity. Now that's a big region, a fairly big region, where the density is a little bigger than the neighboring region. What happens? What happens in a gravitational theory is the opposite of what happens in other kinds of theories. In other kinds of theories, what tends to happen is this: if there's an overdensity here, it will diffuse out and be eliminated. For example, you have an overdensity of ink dropped into water. You have a spot of ink. What happens over time? It diffuses out and disappears and becomes homogeneous. In gravity, the opposite happens, and the argument is very simple. If you have an overdensity here, because gravity is attractive, universally attractive, it will tend to attract the stuff around it, pull it in, decreasing the density outside and increasing it inside. In other words, it's a kind of runaway situation. It's a runaway situation where a little bit of inhomogeneity will tend to reinforce itself. So if you have overdensity, underdensity, overdensity, underdensity, and so forth, in some pattern, the tendency of gravity will be to suck stuff out of the underdense regions and put it into the overdense regions, and thereby magnifying the degree of inhomogeneity. So, the fact that we see inhomogeneity today does not mean that the universe very early was as inhomogeneous as it is today. It must have been much less inhomogeneous, just by running the argument backward. In fact, cosmologists rather early were able to estimate, by running the theory backward, they were able to estimate at the time of decoupling just how much inhomogeneity was there in order that the galaxies could nucleate out of that inhomogeneity. In other words, the picture is the universe was very homogeneous, but little bits of inhomogeneity, little bits of ripples, little bits of excess depletion of some kind. And those overdense regions eventually collapsed by this mechanism, formed galaxies and clusters of galaxies, and the underdense regions formed voids, and that's what we see today. So you can estimate, and it was estimated by people like Jim Peebles and other people, early cosmologists in the 60s, and I'm not sure exactly when, how much inhomogeneity was necessary at the time of decoupling. And the answer was, here's the way you quantify it. You look at the lumpiness and you characterize it by a delta rho, where delta rho is roughly the mean excess density in a lump relative to the background, and you divide it by the density itself. That's the fractional overdensity in a typical overdense region, compared with the density itself. Okay, that's the dimensionless measure of how much inhomogeneity there was. And it was pretty early recognized that this was a number that had to be about 10 to the minus 5. Somewhere between 10 to the minus 4, 10 to the minus 5. All right, so here we were again with the same kind of situation. A question: why is the universe homogeneous? Well, does that really require an answer? It just started that way. But now there was a number. There was a number. In addition to just saying the universe was homogeneous, it is also clear that it wasn't homogeneous. It wasn't homogeneous with a specific numerical magnitude to it. And once you have a specific numerical magnitude, you want to know why that's the magnitude. Now, it's not that we learned why this is the magnitude. We did not. We do not really understand why this is the right number. But the existence of this number focused attention on the question. And the first question was, why is the universe so homogeneous? Later we'll worry about why it's inhomogeneous. The first order fact was that it's very, very homogeneous. The explanation of that today, that is which seemed rather far-fetched when it was put forward by Alan Guth in 1980, was the universe simply expanded by many orders of magnitude. And of course, when something expands, it stretches. And if you stretch out, if you have an inhomogeneous universe with lumpiness in it, and you stretch it out enough, you'll make it homogeneous, at least on the scales that are relevant. So the idea was the universe inflated, which means expanded, and in particular exponentially expanded for some period of time, and stretched itself out so much that it flattened itself to, it's like literally like blowing up a balloon. The balloon is a crinkled, rough shaped thing. When it's collapsed, you blow it up and it stretches out and then flattens out. That's an analogy which you shouldn't take too far. Yeah, no,
How do you explain that it's isotropic? Wouldn't you expect more lumpiness with greater masses in different directions? Why is it isotropic?
It's not well, if we look, I look around this room, it doesn't look isotropic to me. I look out.
A very high level of isotropic.
On an average over large distances.
Yeah.
It's like the surface of the Earth. It's full of hills and mountains and valleys and so forth. You've got to explain those. You explain them by geological phenomena and so forth. But on the whole, the Earth is very smooth. And the universe is the same. If it's homogeneous, or if it's homogeneous, I was going to say if it's homogeneous, it's going to be isotropic. No, that's not true.
What I'm getting at is that wouldn't you expect certain directions to exhibit much greater masses?
Why?
Well, because you start out with a small amount of inhomogeneity, but it's a random process that you would expect that in some directions you would see a great deal more.
No, it's not a random. It's not random. It's not random. I see what you're getting at. You're saying if it were random, you might expect that somewhere out there would be large overdensities if it were random. With some statistical probability, you might find a large lumpiness. It's not random. And we're going to talk about the pattern of it. Basically, it's, it looks like a... Now squeeze this down till it's of size 10 to the minus 5 relative to the background. On the whole, it's very smooth. Right? But nevertheless, there are wiggles in it, and the size of the wiggles are very small. What the implication is, and they're uniformly distributed through space. They are homogeneous, isotropically distributed. There are no tremendously large lumps out there. They're all very small, small in magnitude, not small in size, but small in magnitude. And it's more or less like a very, very smooth Earth with ripples on it that where.
Again, there's an inverse relationship between early time and high temperature relationship.
Mm-hmm.
So there was a particular time when inflation started and stopped, and that relates to particular temperatures. Is there any connection, or is it just random? I mean,
No, it's
is
not
it
random.
temperature causal of the effect, or is it?
During the inflationary period, temperature was not an important aspect of things. During the inflationary period, temperature was not a terribly relevant factor. It was the exponential expansion which was the single most important thing. And I'm going to begin, let's see, where are we? We still have a little bit of time to talk about some preliminaries. It looks like next week will be our real week for inflation and the equations. I'm going to take you through the basic equations of inflation, show you how it works in some detail. But I think what I'll do for the rest of the evening is talk about friction. What does friction have to do with anything? It has everything to do with everything, but tonight I'm just going to tell you about friction. The equations of friction. Write it down because I'm going to use it. And it's very simple. When I speak of friction, I'm speaking of viscosity. I'm thinking about something like a stone falling through a viscous fluid. Why am I doing that? I'm doing that because it will come up. Okay. Take a stone falling through water, or honey. And I'm just reminding you of the equations for it. It's falling due to a force, which is a gradient of potential energy. Let's call the height here, what shall I call it? I'm going to call it phi, which is a stupid name for the height. But it's not a stupid name for a field, and as you might expect, what we're going to be talking about is fields. But nevertheless, the analogy is phi is the height of the stone, and there's a force on the stone. There's a force on the stone which is related to its potential energy. In this case, it could just be the potential energy of gravitation in, but let's just call it a potential energy V of phi. Let's assume the force is downward, which means V of phi increases in the upward direction. And what is the force? The force is the derivative of the potential energy, but minus it, minus the derivative of V with respect, just a derivative, ordinary derivative, dV d phi. All right, let's write Newton's equations now. Newton's equations for the stone, for simplicity, let's just take the stone to have unit mass. Okay. What's the equation of motion? F equals ma. The force on the right-hand side is minus dV d phi. And that's equal to the mass, which I'm setting equal to 1, times the acceleration, which is phi double dot, the second time derivative of phi. Okay, this is F equals ma, and there's nothing special there. In a uniform force field, which would just mean dV d phi is just a constant, the stone would fall with a uniform acceleration, and it would just very quickly pick up a lot of speed and continue to accelerate. All right, that has ignored the viscosity of the fluid that it's moving in, which let's say is something like honey. All right, now that means that there's another force on the right-hand side here. That other force is 0 if the object is at rest. The viscosity exerts no force on an object at rest. It's moving through the fluid, which creates the force. And so the force on the right-hand side is going to depend on the velocity. The larger the velocity, the more the viscosity. And for simple fluids, the viscosity is actually proportional to the velocity itself. So there's a force on the right-hand side which is proportional to the velocity. Which direction is it in? It's obviously opposing the velocity. So it's got a minus sign in front of it here. And there's some coefficient in front of it that's called the coefficient of it. I forget this is the Susskind number. I forget what it's called. I don't know. It's
This is drag.
the drag. Right. Well, what's the letter for it? Who? Anybody know? Who? B? D? Gamma. Whatever it is.
sign can't be the same for both forces.
Why not? Huh?
You want one force to pull it down and then the other force to slow it down.
The v d phi pushes down, right? All right. It's moving with a downward vertical velocity, right? If it's moving with a downward vertical velocity, that means phi dot is negative, right? Minus phi dot is positive. This force is up. As long as it's moving down. As long as it's moving down. Okay. What's that?
The derivative of the potential is the negative of the force. So that's why.
The v d phi is down, is negative. The v d phi is down, is negative. But this one is positive. It's positive because phi dot is negative. All right, it's falling down. All right. So, in the beginning, when the stone starts to fall, phi dot is 0, and basically it starts out accelerating exactly as it would without this. But very quickly, phi dot will increase, and unless as you move down, the force gets bigger and bigger rapidly, this is going to increase because phi dot is increasing until it balances dv d phi. At that point, the forces cancel, and that's called the terminal velocity. In particular, if the force is uniform, if the downward force, for example, like the force of gravity, is uniform near the surface of the Earth, then this is just, let's just call it F minus phi dot gamma. That's the total force. And at some point, it stops accelerating because these two balance each other. And of course, that happens when phi dot reaches the terminal velocity, and the terminal velocity phi dot is equal, let's see, now I am getting my signs confused. The force is negative, right? The force is negative because it's down, but the terminal velocity happens when phi dot is f over gamma. Now my signs are confused. Do I have a problem here? Oh, no, it's okay. F is negative, so the terminal velocity is negative. Terminal velocity is negative because it's falling. All right. That's the basic theory of friction. And what does it do? It slows things down. In particular, if v of phi has a shallow slope, if v of phi, let's plot v of phi. Let's plot phi this way. Let's plot phi plotted horizontally, even though phi is the vertical direction. Let's plot it horizontally. And let's suppose that v of phi is a rather shallow hill. Okay? If it's a rather shallow hill, and the viscosity coefficient here is large, the stone falling along this potential energy here will simply take a long, long time to roll down the hill. That's the situation we will want to be in, and phi will not be a stone. It will not be the position of a stone. It will be the value of a field, but we will want to be in a situation where a field evolves very slowly because of a lot of friction. And that will drive inflation, and we will come to it, I think, well, I don't know, should we go on a little bit? I'm a little afraid to overdo it tonight. Okay, let's go on for a little bit. Let's go on for a little bit. Good, let's go on for a little bit. Okay. Now what we're going to consider is classical field theory. The universe is filled with some field. This field is going to be a scalar field. Now, where does this come from? What scalar field? It was made up. It was simply made up in order to be able to explain the isotropy and the homogeneity of the universe. At the time this was created, it was a long shot, a rather crazy idea, but it seems to be right. Okay, so here's the idea. The world contains, in addition to the electromagnetic field, the gravitational field, and all the usual fields, there's one more field. It's a scalar field, and it's called the inflaton, phi. Why? Because it has to do with inflation. Now, we're going to assume that phi is pretty much uniform in space. We could assume it's not uniform in space, but as the space expands, it will tend to stretch out the variations in phi. So let's just assume, for simplicity, that phi is uniform in space, and think about the energy stored in a field, in a scalar field of this type. Does everybody remember what the energy density of a scalar field is? It contains a kinetic term with time derivatives. This is the energy density. It contains, this is the energy density, let's just call it the energy of a scalar field. It contains one term, which is phi dot squared. This is just the kinetic energy of the field, not the kinetic energy in the sense of movement in space, but the sense that due to time dependence. Then, typically, there is another term which has to do with gradients in space.
So this case, the dot is a partial derivative
With respect to time, it is, right? d phi by dt squared, all right? There's also terms in the energy which have to do with gradients in space. Gradients in space also store energy. But since we've assumed that the field is homogeneous and is not varying in space, which we can justify, but we can do that later, there are no gradients in space. And so this is the only term in the energy density that has derivatives in it. Then the other thing that can be there is a potential energy. A potential energy which is plus V of phi. It's just a thing that's made up, that different values of the field have different energy. Doesn't have to do with derivatives. Just in having a field of a given magnitude, there's an energy density associated with it. That's called the field potential energy. And it's not by accident that I'm giving these the same notation. Phi is a field. Up here it was the coordinate of a stone, but it's not by accident. Okay. Now, let's follow the field, and let's follow it in a box, in an expanding box. As always, the box that we focus on is expanding with the universe. And how big is it at any given time? How big is that box? That box is of size a cubed, the scale factor cubed. Let's say it's a unit box in coordinate space. The size of the box is a cubed. All right. This is the energy density. This is the energy density. So to get the energy, I wrote energy here, but this is really energy per unit volume. If I want to write the energy of the field in the box, I have to multiply it by a cubed but A is time dependent. It depends on time. So we have a time-dependent energy expression, a cubed of t. Kinetic energy plus potential energy. You can think of this, if you like, as formally, mathematically, being the same as the energy of a particle, kinetic energy plus potential energy, except with a coefficient out here which depends on time, something you wouldn't ordinarily write down. You might have a funny situation where the mass of a particle might depend on time, and then this might depend on, but ordinarily you wouldn't write that down. Nevertheless, that's what we have. We have an energy, kinetic plus potential.
Any dependence on spatial coordinates?
Let's assume, on A? No, A is just a scale factor. If there was spatial dependence, we would have to add in here a term for spatial gradients. let's assume for the moment that the field is uniform in space. If it's not, eventually it will be, because the expansion will stretch it out and get rid of the gradients and stretch it out. So it's reasonable to assume that after a period of time, there are no gradients of the field in space.
But I mean, just on a conceptual level, we're thinking of associating this field value with a point in space.
Yes, 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 yes. But if we assume that it's uniform, then all we need to do to find the total energy is to multiply by the volume of the box, which is time dependent.
Is there a question?
Mm-hmm.
Is there any physical thing we can think of for the phi dot? In other words, that kinetic, as you say, is not moving, it's a tiny pebble, but what?
Yeah.
Is there any simple way to think of that? Any physical?
I'm so used to it that I think of it as sort of obvious, but...
What's the field doing in time? Getting stronger or weaker? Or
we're going to find out. We have to solve the equations of motion. That's like asking what's happened to this particle. Is it moving up or moving down? That will depend on the initial conditions. It will depend on how long we wait, and it'll especially depend on the sign of dv d phi, namely the sign of the force.
Whatever's doing it, it's doing it everywhere.
It's doing it everywhere simultaneously. All right? Right. Now we can back off that and study what happens when it's not. But this is the easy problem to study. Okay. Now, how do we find the equation of motion when we know the kinetic energy and we know the potential energy? There's various ways we could do it, but the most efficient way is through Lagrange's equations. Lagrangian, let's write the Lagrangian now. The Lagrangian is the difference of kinetic energy and potential energy. So you pick up your copy of the theoretical minimum and you look up Lagrange's equations with this. Phi is like the coordinate, and here is the Lagrangian. The only new thing that wouldn't be there for an ordinary particle is this A of t. All right, so let's work out Lagrange's equations. The first term is d by dt, or I suppose we can make it d by dt of partial of L with respect to phi dot. Everybody remember that? And what's on the right-hand side? Right. That's Lagrange's equations. So partial of L with respect to phi dot, this is the equation that we get out of it. Partial of L with respect to phi dot is just phi dot times a cubed of t. This is partial of L with respect to phi dot. Without this isn't t yet. dl by d phi dot is phi dot times a cubed of t. Is that obvious? Good. Now, now we have to take its time derivative, d by dt. And that we have to set equal to a cubed times minus a cubed times dv d phi. Or just ordinary derivative, dv d phi. We could call dv d phi, we could call it the force. So minus dv d phi, we could call it the force. But notice that there's this extra explicit time-dependent thing there. This doesn't quite look like Newton's equations. It would be Newton's equations if A was constant. Okay? But A is not constant, so let's work it out and see what it is. First of all, the d by dt, there are two terms. One comes from hitting phi dot, the other comes from hitting a cubed. So let's first do the first one. The first one is a cubed times phi double dot. That's d by dt of phi dot times a cubed. And what's the second term? It's phi dot times the time derivative of a cubed. Okay? The time derivative of a cubed is 3a squared times a dot. Do I have that right? Yeah. That's in a parentheses over here. And that's equal, let's just call it to a cubed times the force on phi. Okay. It's very tempting, and I will do it, to divide out the a cubed, since it appears both here and here. Let's divide out the a cubed. But I better divide over here also, huh? Okay. So let's clean it up. It's phi double dot plus 3 a dot over a squared divided by a cubed is 1 over a, so it's a dot over a times phi dot is equal to f. What is a dot over a called in cosmology? The Hubble constant, which is not generally a constant, but it's h. It's, of course,
Isn't it supposed to be like the same everywhere, though?
everywhere's in space, but not necessarily in time. May be the same in time, but it may not be. All right, so we'll come back to what it is in time, but keep in mind, it could be time dependent. Phi double dot. Phi double dot from here plus 3h times phi dot equals f. Let's write this one this way, plus equals f. This is exactly the same equation as the falling stone with a viscosity coefficient 3h and a force which is just a gradient of v. So our model for the way this field evolves can be envisioned by just supposing that phi was the position of a particle on a hill where the height of the hill was v, or the gradient of the altitude of the hill was the force, dv d phi. A ball rolling down the hill, except that there's a viscous drag force proportional to the Hubble expansion rate. So the Hubble expansion rate behaves as a kind of friction. All right? That is why we went through this exercise over here. If the Hubble friction is strong, if h is big, and the force here, and if the hill is reasonably flat, not terribly flat, but somewhat flat, then this could be like a ball moving through motor oil in Wisconsin on a cold day. Okay? It just left to its own devices without the friction term, it might roll down the hill in a few seconds. All right? With a large friction, it could take years to roll down the hill, depending on the magnitude of the friction. So this is called the cosmic friction term in the equation of motion of a scalar field. And it has the effect, it has the simple effect of slowing down the evolution of the system and keeping the ball from rolling down the hill. The next time, we're going to use this to study the cosmology of a universe which contains a field like this. In other words, we're going to look at the the Friedmann equation with an energy density which is given by this. All right, so we're going to study how the universe expands and evolves under the influence of an energy density which is slowly rolling down the hill here. That's the phenomenon of inflation. That the way the universe responds to this very small, slowly moving field. Okay, next time.
For more, please visit us at stanford.edu.